any study of dynamics is incomplete without actually looking at Newton's laws of motion. And if you're going to look at Newton's laws of motion, let's look at them properly. There we go. Corpus omni preservari. Anyone still doing Latin?
Of course.
No? Anyone did Latin beyond year 7? So you did it in year 8? Oh, well then you should be able to translate for us. So everybody, corpse. Okay. Preservari, preserves. Let's have a look at what the first law actually says. So everybody continues in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. It just means in a straight line. Right? Yeah, so you're not deviating off the path or anything like that. So basically that's just saying, hey, if I'm standing here and I'm still, well, I'm going to stay still unless some force is put on me. But similarly, if you are physically moving, you'll stay moving again unless some force. So that's basically the first one. The second one, of course, is the one, the most famous of them all. Motus proportionalium. Right? So what it's basically saying is, all right, so now some force is being impressed upon it. So law 1 says it'll stay at rest or unless some force is impressed. So we're saying there is going to be a change of motion. There's going to be a change of motion, and it will be proportional to that force, the motive force, impressed, and is made in that direction of the right line that it is impressed. So in that direction. Basically saying motive force is proportional to change in motion. Well, change in motion, change in velocity, is acceleration. So force is proportional to acceleration. So it's got to equal some constant times acceleration, and we come in with that well-known formula: force is mass times acceleration. So that's our second law. Third law, actione contrarium. Often misquoted as to every action there's an equal and opposite reaction. Or, sorry, not misquoted, but often summarised as. But what it actually says, to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed in contrary parts. I suppose the simplest explanation, I'll go back to me standing here. Right? And the question is, why aren't I collapsing because of gravity? Because there is a force balancing out. There actually is a force of the floor, if you like, is applied on me, and that is balancing. So everything works nicely. I don't collapse. Okay, now, so these reaction forces will come into play, certainly in circular motion they'll come into play. So let's talk a bit about acceleration then. What we've seen so far. Acceleration, second derivative with respect to time, that is of displacement, or the first derivative of velocity with respect to time. So, okay, that's when we got it as a function of time. We then have seen d dx of a half v squared when it is a function of x. The other one, which I also used before, v to v dx, but this is also handy because, yes, acceleration could be a function of velocity rather than displacement or time. In that case, v to v dx could come in quite handy. A very, very old question, but I just love showing it. Assume the Earth is a sphere, radius capital R, and then at a point little r, which of course is bigger than capital R. Huh? Wouldn't you think bigger R was big? Anyway. From the centre of the Earth, the acceleration due to gravity is proportional to 1 on r squared and is directed towards the Earth's centre. A body is projected vertically upwards from the surface of the Earth with initial speed capital V. Prove that it will escape the Earth if, but only if, that velocity is greater than or equal to the square root of 2gr, where g is the magnitude of the acceleration due to gravity at the Earth's surface. It's always a good idea with these questions to draw some sort of force diagram so you get a feel of what's happening. The blue circle there is representing the Earth. The red line is the direction I'm going to travel. There's good old Bob. Bob's going to become our friend in this topic. We're going to see him a lot. Okay, at the Earth's surface, we know r is equal to capital R. The initial velocity was capital V, and they've told us the acceleration due to gravity was g, directed towards the centre. So I'm going to say going down is negative. I think that's negative. What else do I know? I know that if it ever stops, velocity would equal 0. So the greatest height would equal 0. So what's happening with Bob? What forces are coming into play? And this is how we should approach our extension 2 problems. We start every problem with thinking about what forces are acting on Bob. There's only one force acting on Bob in this question, and that's the force due to gravity. This force that I've just drawn in is not a force. It's a resultant force. See, what you need to work out is what is the result of all the forces acting on Bob. So actually it's probably not correct for me to draw it in my force diagram. Resultant force, basically you define which direction you want to be positive. So as long as you know which direction you want to be positive. The red ones are going to be all the forces acting on it. And the only force acting on it is the force due to gravity. The acceleration due to gravity is proportional to 1 on r squared. So the acceleration is equal to some constant on r squared, which means the force is equal to mass times the... So that's why I have written it as m mu over r squared. There's my equation I can start with. There's only one force. It's in the opposite direction to what I'm calling the resultant force. Well, the m's will cancel. There's my acceleration. It's in terms of displacement. It's in terms of displacement. Now, I can work out mu from other information they've given me. They've told me that when r is r, that's bigger, and acceleration is minus g. Subbing that in, I get that mu is actually gr squared. Gr squared. So there's my new acceleration equation, minus g r squared on little r squared. Okay. I'm going to use v to v well, r in this case, because we're using r to represent displacement. So v to v dr, separate my variables. They told me the initial velocity was capital V. That happened at the Earth's surface, which was capital R. So I'll match those up. I'm going to come up with an equation that links little v and little r. I've factorised out the minus gr squared because that's a constant. So all I'm integrating on the right-hand side is dr on r squared. On the left-hand side, it's v. So I'll end up with v squared. Notice instead of saying half v squared, I've multiplied the other side by 2. So I have 2gr squared times 1 on r. Little v squared minus capital V squared is equal to 2gr squared on little r minus 2gr squared on big R. There is a velocity equation. V squared is 2g big R squared on little r plus big V squared minus 2g big R. It's about now you've probably forgotten what the question actually said. We had to work out its escape velocity basically. So there's different ways of thinking about it. I've said, well, if my particle never stops, so it escapes, then I know that displacement is going to approach infinity. It's never coming back. So if I find the limit of my velocity then, as r approaches infinity. So limit of the velocity, well, little r is only one spot and it's on the bottom of a fraction. If I divide by, well, theoretically divide by infinity, I'm going to get 0. So hyperbola, as we approach infinity, the y value is approaching 0. So I'm left with v, capital V squared minus 2gr. Now I know little v squared is always greater than or equal to 0. So therefore, capital V squared minus 2gr is always greater than or equal to 0, which means that initial velocity must always be greater than, velocity squared must always be greater than or equal to 2gr. Therefore, in order for it to never stop, I must have an initial velocity squared that is greater than or equal to 2gr. In other words, velocity greater than or equal to the square root of 2gr. Then the particle never stops, i.e. it escapes the Earth's atmosphere. Thank you, calculus. We now know how fast to send our rockets up. Now we have a real fun bit. Let's assume we're sending it off with that velocity of the square root of 2gr. We're now going to find the time it takes to rise to a height of capital R above the Earth's surface. Remember, we got our formula, little v squared is 2gr squared, etc., etc., etc. We're trying to find a link between velocity and time here, are we? We'll displace. Capital V, we're setting as the square root of 2gr. That makes life easy because look what happens. I've now just got v squared on 2gr squared on R. V will be the square root. Remember, it's never coming back. We're setting it off with an escape velocity. Therefore, velocity is never going to be negative because it's never going to stop and come back. So now I'm going to take the positive square root in this case. Trying to get that link between displacement and time. So dr dt, let's integrate. Turn it upside down. Separate my variables. Remember, I'm going from the Earth's surface, which was big R, to big R above the Earth's surface, so 2R. So I'm going from R to 2R. 1 on the square root of 2gr squared, again, is just a constant. So all I'm really integrating on the right-hand side is the square root of R. So there is the time it takes. Yes, I've got to sub in and calculate this, because remember, they've said show it's a particular amount. So let's play around with it. If I sub in 2R, remember, R to the power of 3 on 2 is R root R. So if I sub 2R in, I get 2R root 2R. And sub capital R in, I get R root R. Over here, I've taken out the 2/3. So the 2 cancelled with the square root of 2, leaving me the square root of 2 on top. And the 3 came out, and I got root gr squared. I'm keeping one eye on what I'm trying to prove here. So if I factorise out the R root R, inside I'm left with 2 root 2 minus 1. And also the square root of R squared in the fraction, I can make R. Well, that R will cancel with the other R. So I now have the square root of R over 3 root G, but now I've multiplied the root 2 inside the parentheses. And that got me 4 minus root 2. Are we getting close to what we're trying to prove? If I rewrite that, make it all 1/3, I get root R on G. I think that was it. Okay, so we have proven what it is they asked us to do. Time taken to rise to a height. All right, that's just a little introduction there to scare you a bit. So we have Patel 8, so I just picked 3 out of that, and then some out of 4A.